Hey there, everyone. Brian Scholl with Straight Data Science brand. So today, and the topic I want to talk about is principal component analysis, and I'm going to try to explain this to you so it's very easy to understand how this concept works. So PCA basically is a dimensionality reduction technique. So you have a lot of different dimensions. You can have a dimension could be basically a feature or a column, right? Or you can have a bunch of different features and columns, and you want to try to understand which column or which feature has the most impact on the dependent variable which you're trying to predict, right? So we take this machine learning tool, feed in a whole bunch of data into the thing, right? Using a lot of columns and make a prediction on one single column. So I'll show you in just a minute how that is going to work, right? But basically we want to reduce everything in the whole feature space to two components and capture as much variance as we can. So variance is what? It's information, it's data. We want to see which components here have the most statistical influence on the target variable. So I created a hypothetical data set here. I don't have this actual data, and this is proprietary about loans, but I'm going to get some realistic features here and feed this into the model. So credit score is going to be important, right? When you're issuing loans to clients, debt to income ratio, loan amount, interest rates, employment length, delinquency rate, that's very important, revolving balance, annual income. And then we're going to create our own default probability, right? This is a calculated or derived column, and then we're going to try to predict defaults, right? Given all this information that we're feeding into the algo. So I'm going to go ahead and run it, create the data frame, so that looks good. So I'm going to go ahead and run this next cell right here and use all of these different features, these two that I just created. Not that one, I'm going to keep that on the side for just a minute. I'm going to load in all these features. This is the calculate feature, right? And I'm going to try to predict default. So the default is going to be the target variable. The target is the y. The x variable is all the independent features, right? Which includes the logit. I'm calling this a logit, and this is a feature that's created or composed of credit score, debt to income ratio, loan amount, interest rate, delinquency rate, and annual income, and assigning a small probability or small calculation to derive this logit number, okay? And we're going to use this to help us to predict default. So if you don't have a column that is important to making these predictions, you can just create your own column, right? That's called feature engineering. So that's what this cell does. Control Enter to run it, and this is done. Let's take a look at the PCA features here. So we have PC1, principal component 1, and principal component 2, and then the probability of default. Okay, so this is all we need to make all our predictions. So this is pretty cool. Let me run the next one here, and we will create a chart, right, just to see what is the probability of default. So 0 is no default, 1 is default. These things are always binary, right? So binary, true, false, yes, no, on, off, 0 and 1. So 0 is fine, there's no default. 1 is a default, and you can see there's a few of them in here, but primarily these loans are not being defaulted, right? There's a handful, but for the most part, we're fine. And that's what you want to do too, right? Because you want to make loans to a lot of different customers or people or small businesses, right? If you don't make any loans, you're not making any money, right? You're not going to have any revenue on your books. If you're loaning to everybody in the world, probably a lot of people are not going to repay those loans, right? So you try to lend to as many people as you can, but not overextend yourself or lend to too many people, especially people that have bad credit or some kind of impaired ability to repay that loan, okay? So let me do one more calculation here to get the to map everything back to the original components that we're looking at, right? So we created PCA. If you look at this right here, we have the principal components, right? 1, 2, and then all the components. I'm just showing the first 5 by default. The head shows the first 5 records, right? And we start with 0 and then 4 because Python is 0 based. So remember, this is what we started with: credit score, debt to income, loan amount, interest rate, employment length, delinquency, resolving balance, annual income, and default probability, right? So those were the inputs. This is the analysis right here, principal components. We want to take that and map that back to the original features that we fed into the model. So I refresh the cell and I can see the features and I can see the chart. So this is where it gets very interesting. So we can see if credit score is negative, and the more negative it is, the more likely you are to be able to predict the default probability, right? So if you have a huge negative credit score, you're not going to loan money to a certain individual or a certain entity because they're not going to be able to repay the income. So debt to income ratio, if that is negative, you're not going to make the loan, right? It makes no sense. If the loan amount is negative, in this case 0.36, let me see if I can see that. Yeah, it's right here. So that's the 0.36, negative 18.50. That's the credit score. If these are all negative or um, somehow compromised or impaired, you're going to know that these have a statistical influence on the target variable, right? And you can see we set the target variable right here to default. We're looking at the probability of default, right? I'm sorry, this is the target variable, right? This is a y variable is the target, and the independent variables are all the other variables that have an impact or some type of influence on the target, right? So we go back here. So employment length, the longer the employment length, the more likely the person is able to repay the loan, right? If they've been at their job for many years, that's probably a safe bet that the person will continue to stay there. Although in this economy, who knows? I mean, you hear some crazy things in news all the time, people getting laid off. But anyways, I mean, that's a whole nother video. I have another video on that. Okay, we don't have to go down that tangent. So delinquency rate. So if delinquencies are rising, if that's up, that has an influence on the target variable, which is the ability to repay the loan or the default, right? Revolving balance. If there's a larger revolving balance, then there's more capability to repay the loan. And annual income. As your income goes up, better ability to pay the loan, 0.55, and that corresponds to the 0.55 over here. So that's principal component number one. For number two, we have another plot down here, okay? And we can interpret that like this. If I refresh the cell, Control Enter to refresh, and you can see as credit score goes up, the probability to repay the loan increases. Debt to income ratio, if that increases, that's going to have an impact on the default rate. Loan amount is going to have an impact on the default too, right? If people borrow more and more money, they might not repay that money. If it's a small amount that they're borrowing, a few thousand, 10,000, it's probably going to get repaid pretty quick. If they're borrowing 100 million, it's probably not going to get repaid, right? So the loan amount has some impact on the probability of default. The interest rate has a huge negative impact. If I go back over here, negative 0.55, that's what we're looking at. The interest rate has a huge negative impact for principal component number two. Employment length, that has about 0.20 impact. Delinquency rate really doesn't have any impact at all, and annual income doesn't in principal component two, but in component number one, that was the biggest actually. So it's interesting. And then revolving balance, this is the largest for principal component number two, and revolving balance was somewhat influential in predicting the target variable, but not huge for principal component number one. So this gives us, this tells us a few different things. The mathematical basis, basically, we use eigenvalues to decompose a single value to find principal components, like what are the main components that have an influence on the target variable, that probability of default, right? And maximizes the variance of this data set. So we look at what has the most divergence or the most, oh, I forgot the terminology. I forgot the term. Sorry. What has the most variance or the most orthogonal, the most orthogonal projection? So orthogonal projection would be like opposites, right? So if something points over to the right, something points upwards, or something points left and something points up or down and left or something like that, it's called orthogonal if it's pointing in different directions, right? So there is some influence. It's not exactly opposite. Exactly opposite would be going to the right, going to the left. But if you're going to the left and up, or going to the left and down, that would be considered orthogonal, right? So that's what we're trying to see, these patterns and these relationships between all the features in the data set and the target variable. So this projects data into a lower dimensional space. So we have this high dimensional space with a lot of stuff going on. It's very complicated, but we distill it down or boil it down to a lower dimensional space so we can see the significant principal components here. This reduces the dimensions of data and helps us to focus on class separability. Remember, we're not going in opposite directions. we're looking at like a 90-degree angle. So up and to the right, or up and to the left, or down and to the left, down to the right. PCA can be used as a pre-processing step to reduce noise, or clear a whole bunch of big dimensions and get down to just a few dimensions, fewer dimensions, right? This is dimensional reduction, so we can see what has the biggest impact on the target variables, right? This is commonly used for visualizing high dimensional space. So you can plot a 3D chart, you can plot a 2D chart, but you can't really plot a 4D chart or 5 or 6. I mean, there's kind of a few ways to do that, but then you're using different characters on the chart to represent different things. So it gets very complicated if you have a high dimensional data set to do your plots. After 2D and 3D, it gets more complex. You can do it, but if you have dozens of different dimensions, can you even plot that? And is a human being going to be able to interpret that? Probably not. And this basically highlights patterns and structures in the data based on the overall variance in the data. And again, variance is information, right? So we want variance, but we want to take all of that variance and distill it down into the fundamental components so we can understand the story that the data is telling us and make more informed, more intelligent decisions. So that's it. I'm going to wrap it up here. Hopefully that was enlightening. Hopefully that was useful for you guys. I always try to make my videos practical and useful too, and just do a big knowledge drop and show you how this stuff works and break it down into a simplified, clear example. So hopefully I was able to achieve that goal today. Okay, I'm going to wrap it up, and I will see you guys in the next video. Bye for now.